Hello, this lecture will cover pages 95 through 104 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 7H, Second Order Circuits, Working Problems. If you remember the last lecture, we went ahead and we developed the response equations for second order systems that had RL and C elements in them. And we said that the differential equation, the analysis of the differential equation would lead to a characteristic equation. This is on page 92. And in this characteristic equation, we took the exponent of the coefficient of the S term, and we set it equal to 2 zeta omega 0. We took the constant term in this second order system, omega 0 squared, and we defined zeta as the exponential damping ratio, and we defined omega 0 as an undamped natural frequency. Well, if you solve the characteristic equation, which is what we're going to do here in 3 examples, and you look in terms of its values, we said that using the quadratic formula, you got S1 and S2 to be equal to natural frequencies. And I used the quadratic formula to define this, but you could factor. I mean, if you could factor that expression, the characteristic equation, you could pull off the natural frequencies directly, and we're going to do that in one problem in a minute. And we said in general, the transient solution, and that's all we're interested in, is the short-term transient solution in these second-order systems, was equal to K1e to the S1t plus K2e to the S2t, where S1 and S2 were the solutions to the characteristic equation, which we defined as natural frequencies. And then if you evaluate this at x equals 0, you get K1 plus K2, and if you take the derivative of this expression up here and evaluate it at t equals 0, you get S1 times K1 plus S2 times K2. And you just evaluate these simultaneously to get the complete solution. The K1 value comes from these equations, and the K2 value comes from these equations. And you have your complete solution that you can evaluate at any time what the voltage or current is in a circuit. Now, we're actually going to work some problems here, and we're going to start out on page 95. I said there was 3 cases. There's the overdamped case, there's the underdamped case, and there's the critically damped case, and you could find those. You can determine what case it is by first finding what zeta is. Well, case number 1, if zeta was greater than 1, it's overdamped. If it's overdamped, the roots, S1 and S2, were real and unequal roots. And you get this expression right here for your solution. And you simply have to evaluate this, okay, at t equals 0. And at the derivative with respect to time, evaluate that at t equals 0 to get the complete solution, to get your K1 and K2 terms. These exponents you get directly from the characteristic equation. You'll see that in a problem in a minute. And that's the general form. Well, it's difficult to look at that form. That's why I put page number 98 in your lecture notes, because this is the equation here. If you recognize it's an overdamped case is when zeta is greater than 1, you can go straight to this equation here. Make sure you understand this equation. I tried to get it in here in Word, but it's in your textbook. If zeta is, case number 2 said if zeta is less than 1, that's an underdamped case. Well, if zeta is less than 1, the roots, S1 and S2, are complex conjugate roots, which makes the transient oscillatory. That's what gives you the overshoot and your undershoot, and your overshoot and undershoot to the response I was talking about. It's oscillatory. And this is the form of the equation. That's your solution. And you just plug in the values of zeta and omega 0, and you get your exponents on E. I want you to notice here that when you work out the quadratic formula, you're going to see that you get complex conjugates because zeta is less than 1. So we don't use this form too often. We really don't use this form too often. What we do is we use something called Euler's equation. And this is what Euler's equation looks like e to the plus or minus j phi is equal to the cosine of phi plus or minus j the sine phi, depending. The sign depends upon if this is a plus exponent, you get a plus there, and if this is a minus exponent, you get a minus there. You're not responsible for that, but I used Euler's equation and I substitute it back in here. And what I end up with is this form, and this is the form you'll be responsible for, because I think you can see both components in an oscillatory system. The solution is purely transient. Don't forget, we're just working out the homogeneous equation, which is equal to e to the minus zeta omega 0 t. That gives you your decaying envelope. In a system, look, that gives you your decaying envelope here. That's what that e term does. Or this decaying here, that exponential decaying at that point, that comes from this term. And here's your oscillatory terms. A1 cosine of omega d plus A2 sine of omega d. And I'm just getting rid of a lot of these different values in here, and I'm just referring to this as omega d. Or am I getting that? On the previous page, I just defined something, and the author does this too, where if you take omega 0 times the square root of 1 minus zeta squared, if you can find that value very carefully, that's just omega d, and that's called a damped natural frequency in radians per second, as opposed to the undamped natural frequency we talked about before. So omega d is defined as omega 0 square root of 1 minus zeta squared. That just makes this a little easier to look at over here. That's all. So you have an A1 cosine of omega d plus A2 sine of omega d times t in both cases here. Now, I'm calling this A1 and I'm calling this A2. I'm not calling it K1 and K2 because the K1 and K2 terms we're strictly using when you get case 1, so we don't mix up values here as we go. When you see a K1 and K2, that's the overdamped response, and when you look at A1 and A2, you know you're talking about the underdamped response, case 2. And again, you have to evaluate this, where A1 and A2 are found from the initial conditions. You use your initial conditions. I mean, that's part of the solution right there. You just plug in omega d and zeta omega 0, and you get an exponent. Oops, you get an exponent up here, and you can go ahead and you can get in your radians per second right here, times t. But you don't know what A1 and A2 is. You don't know what these leading coefficients are here. Well, how do you find those? Well, you get them from the initial conditions. Voltage at 0 or current at 0, and the derivative of either voltage or current at 0 evaluated at t equals 0. We're going to have to do this in some cases to get the complete solution up here. I want you to notice that I'm showing you here to a decaying exponential, what it looks like. It has ringing. Well, you know why it's ringing, because you get a transfer of energy between the systems, between the components. And the reason it's decaying is the resistor is eating up that energy. And down here, if you have a step response and you have a final value, I want you to notice that we have a transient here. There's our transient. That's what we're concerned about. Then we got a steady state solution. So the final solution turns out to have a steady state value plus a transient. And then finally, case number 3, where zeta is exactly equal to 1. It's critically damped. You've had each one of these cases when you've taken Algebra 2 or second course in algebra, where you either had, in this case, repeated roots, or you had complex roots, or you had unequal roots that were real. That was the first case. So it's the same thing. So critically damped, zeta is equal to 1, and you're critically damped. S1 and S2 are repeated roots, and they're equal to minus zeta omega 0. That's what they're equal to, and they're repeated. Well, the form of that response, when you notice zeta is exactly equal to 1, is the value, the complementary solution, or the transient solution with respect to time, is equal to B1. Notice we're not using K's, we're not using A's, we're using B's here. B1 e to the minus zeta omega 02 plus B2 times T e to the minus zeta omega 0t, where the B1 and the B2 are found from these initial conditions again. Now, each one of these cases 1, case 2, and case 3, there's the formulas for them right here. You can see them down here. Well, here's your overdamped. Okay. Here's your underdamped, where we defined omega D, the damped natural frequency, equal to this. And here's your critically damped solution. I just put them here so it's easier to see. The remaining second order problems in chapter 7 will be easy for you to read, and will be easy for you if you read and follow the procedure on the next page, which is this procedure right here. So again, we have another procedure. We're going to do step 1. I want you to read it. We're going to do step 2. I want you to read it. From step 2, you go to step 3. And once you recognize whether zeta is greater than 1, zeta is less than 1, or zeta is equal to 1, I'm going to allow you to go straight to these equations. And you get the form of the answer. But then to get either K1 or K2, or A1 or A2, or B1 or B2, you have to evaluate initial conditions. That's in step 5. 2 initial conditions, either given or derived, are required to obtain the 2 unknown coefficients in the system response equation. That's the last step. Probably the most difficult, but I'll show you how to do it. At minimum, you should be able to get the general response equation based on zeta. And then step 5, you're either finding K1, K2, or you're finding A1 or A2, or you're finding B1 or B2. That's the last step. So we already talked about page 99 and what it represents. We always talked about page 100 and what it represents. So that's going to take us over here, and we're going to look at 2 problems here. We're 12 minutes into the video, so let's see if we can't look at these problems now. Example problem number 1. I want you to find the voltage via T for T greater than 0, and here's the circuit. I want you to find the voltage at this node right here. And initially, that switches in position number 1. And we're going to throw it to position number 2 at T equals 0. So if you just look at this, and we're going to go by the initial conditions we would have here. VC is 0 is going to be equal to 4 volts. And I think you can see that. When it's in position 1, the voltage across the capacitor, it's charged to 4 volts. So there's an initial condition for VC is 0. And the derivative of VC is 0 dt is equal to 0 volts. The rate of change of that in this system within position number 1, there's no rate of change. Okay? So it's 0. So what we always need in second order systems, and you're going to have to recognize this in every system, we need to have VC at T equals 0. We got it. VC at T evaluated at T equals 0 is 4 volts. So I'm giving you that. We got that. And we need the derivative of VC at T with respect to T evaluated at T equals 0. And we got that. So in this first problem, I'm giving you both this and I'm giving you this. Now, why are we looking at that again? Because when we look at the solution to these problems, all of them, if you take a look, they all required, once you get the general form, you need to find that value, whether it's current or voltage, depending upon what I'm asking, evaluated at 0, and the derivative of that value, and evaluated at T equals 0. You're going to have to find these in both cases if I don't give them to you. That'll give you the second half of the solution. Because you're going to get the expression based on zeta. You'll be able to get that. But you're not going to be able to find your constants, whether it's K1 or K2 or A1 or A2 or B1 or B2, unless you evaluate these. Hope you see that. So again, if you're in position number 1, the current through the inductor, initial condition is 0 amps. There's no current going through it. So by Kirchhoff's current law in this system up here, there's the expression. In the time domain, we're going to write that, and you should be able to do that. You should be able to get to this point right here. If you don't see what's happening here, look at see lecture notes, page 89 for the analysis up to this point right here. Because that's the circuit we had. So you end up with this differential equation. and we're going to solve the homogeneous equation equal to 0, because we're only interested in the transient here. The characteristic equation you can get from the differential equation. There it is. Can everybody look at that time domain equation and get into this complex frequency, or this frequency domain, with this s parameter? S squared plus 2.5s plus 1 equals 0. Now, once you have the characteristic equation, what you need to do is you need to find omega 0 and zeta. Well, the first thing you really have to find is omega 0, so you can find zeta. So here's how you're going to do that. You know that the coefficient on the s term is 2 zeta omega 0, which is equal to 2.5. So I'm saying 2 zeta omega 0 equal 2.5. Look back in your lecture notes. You'll see where we defined that. What page was that on? I think we defined that back on page number 93. Or page 92. Page 92. So we end up with omega 0 equal 1 radians per second. 1 radian per second from that characteristic equation. That allows us to move over to, therefore, zeta is equal to 2.5 divided by 2 omega 0. So now we can find zeta. Zeta is 1.25. Now we found zeta. That is very important. When you see zeta is equal to 1.25, it's greater than 1. Therefore, you're at the overdamped response. We know we can go straight to the overdamped response, and it's going to look like that, not oscillatory. So we can plug in the values up here to the equations that I gave you back on page number 98 in your lecture notes, and you can calculate this to be a -2 and this to be a -1.5. So there's part of your solution right there. Now, you could get to this point another way. I think everybody could probably look at this equation right here, okay, and you could factor that equation. Sometimes you can do that. Can everybody factor that equation right there and see that is s plus 2 times s plus 0.5. So I just factored that equation. If you take a look at that and multiply that all out, you get this. So what are s equal to here? The roots of that are s equal -2, s equal -0.5. And I put it into the equation. Now, not all of them are easy to do like that. I mean, not all of them are going to be that easier. So just go through these procedures. Just go through this procedure here to find omega 0 and zeta, and you're going to end up with the same result. So now what you have to do is you have to use the initial conditions to evaluate for K1 and K2. So VC is 0 is equal to 4 volts. And take a look at this. Evaluate this at T equals 0. You get K1 plus K2. Well, that has to equal 4 volts because that's your initial condition. And then the derivative of voltage with respect to time evaluated at T equals 0, I want you to go ahead and take the derivative of this. Take the derivative of this equation, which I did, okay, and evaluated at T equals 0. So there's my two equations with two unknowns. So K1 is equal to 4 minus K2 from here. Make a substitution. You can see K2 is equal to 5.33 and K1 is equal to a negative 1.33. So here's my complete solution to the problem. V of t is equal to minus 1.33 e to the minus 2t plus 5.33 e to the minus 0.5t, and that's in volts. Most of the time, we will be given the initial conditions of the storage elements. And it's gonna influence your final answer. I'm going to show you that in the next example here. In this case, we had voltage across the capacitor, but there's no current through the inductor. If there's current through the inductor, that's going to make this problem change quite a bit if there was an initial condition there. I want you to be able to analyze that. But here's the solution. Now, if you go back and you let t equal 0, and you let t equal 0 in this equation, it should satisfy the 4 volts. Because we know VC as 0 has to equal 4 volts. Well, does it? Well, sure, you get a minus 1.33 plus 5.33, so that initial condition is satisfied. You should always check that real quick. You get 4 volts. So I can give you, in this example, any time period. I can give you any time period after t equals 0, and it'll tell you what the voltage is at that point. In this case right here, keep in mind it's overdamped. It's not ringing. But even if it was, it'll give you a point anywhere. It'll give you a point anywhere on that curve at that time based on that. And then finally, example problem number 2. The same problem, but we're going to have initial conditions. Keep in mind, we need VC at t evaluated at t equals 0. It's given. And we also need the derivative, rate of change at t dt. Well, I'm changing the problem. It's not 0. I'm going to tell you that you have the current through the inductor initially is minus 1 ampere. It's come from another source. Don't look at the original circuit and try to see that. I'm just telling you, I'm going to give you an initial condition for the current flowing through that inductor. There's an initial condition here where there's current flowing through that inductor. So, the derivative of the voltage across the capacitor with respect to time is not equal to 0 because there's a current going through the inductor. So we have to determine VC is 0 dt from the information given. Well, by Kirchhoff's current law in the circuit, IC plus IR plus IL equals 0. I wrote those equations here and I end up with this. I end up with this equation right here. You can see that. We've done that before. There's my derivative of the voltage with respect to time is equal to minus 1 over RC via T minus, there's the current IL at T divided by C. I'm just getting that from this differential equation right here. Now I have something that I can evaluate up here for initial conditions. At T equals 0, I think it's pretty easy to see. Plug it in up here. VC at t equals 0, the derivative change of the voltage with respect to time evaluating at 0 is minus 5. Okay. Down here, go up here again and take the derivative of the initial equation. The derivative of the initial equation, dt, evaluated at t equals 0. I think if you plug in RLC and a C here, you can get this equation here. You get this, it's equal to a minus 5. So now you have two equations here. You have this negative 2 K1 minus 0.5 K2 equals a minus 5. All that's coming from here, from that equation. Okay. And the initial observation, K1 plus K2 equal 4, comes from this. So we end up with K1 equals K2 equal 2, and this is what we end up with down here for our final value for voltage. V at t is equal to 2e to the minus 2t plus 2e to the minus 0.5 t volts. Take a look at that same problem except different initial conditions. That is the solution to this problem number 2 whenever we have these initial conditions, and the solution we had to problem number 1 with those initial conditions look like this. Notice at t equals 0, this gives you 4 volts, and it should. Notice at t equals 0, this is going to give you 4 volts, and it should. But what happens after that's completely different, because up here we had initial current in the inductor. And then example problem number 3. Here what we have is a differential equation. I want you to find the network's characteristic equation, natural frequencies, and the general form of the network transient response in terms of K1 and K2. You do not have to solve for K1 and K2. I just want you to keep in mind, I just want you to give the general form of the voltage. You don't have to solve for K1 and K2. And I want to see what you end up with there. And when you're done, try that on your own. You should get this. There's the characteristic equation. I found the natural frequencies. Notice they are real and unequal. I didn't find zeta in this case first. I went right to using the equations I gave you in the book, in the lecture notes. I ended up with S1 equals 2 radians per second. S2 is minus 1 radians per second. But I think you could see that right here. We could factor that to get this. And here's my expression. Notice that the response via t is equal to the transient solution. Why? It's a homogeneous equation. All we're interested in is a transient response. That's why the complete solution is purely transient. And this is what it looks like. It's an unstable system, but I still want to show it to you. It's unstable in this case. Because notice when t gets larger and larger and larger, this goes away, but it doesn't. It grows exponentially because of this term. That's a plus right there. We'll work more problems in the next lecture. That concludes this lecture.